Hello, everybody, and welcome to another wonderful day of chemistry. So today we're going to be talking about that good old favorite topic of atomic structure. So I do want to note that this is going to be a brief overview of atomic structure, and later in the semester we're going to kind of dig down a little bit more into some of the nitty-gritty details. But in order to talk about chemical reactivity, we first really need to understand what an atom is. And it turns out a good way to do this is going through the historical models. Now, it's worth noting that some of these models on here are jokes and some of them are real, and it can be a little hard to figure out which ones are which. So, in order to first understand the structure of an atom, we first need to know what the parts of an atom are. And the three major constituent parts of an atom are the electron, the proton, and the neutron. So the first one of these that was really well understood was the electron. And one of the reasons why is because of electricity and electronic charge. So electrons were first really observed because you can build up a negative charge on an object, and then you can suddenly allow those electrons to flow back to an item with positive or even neutral charge. And if you want to see a great example of this, go ahead and shuffle your feet on some carpet and then touch a metal object. By shuffling your feet or building up that static electricity, you're unevenly depositing negative charge on an item, often yourself, occasionally, say, a piece of cloth that you're wearing. By building up a slight imbalance of electrons, you can then watch an arc as it goes back to a more neutral object. Now, one of the things that is worth noting is that it's very hard to build up a large electronic bias. And even a small electron unbalance of negative charge can contain a lot of energy. And this is going to become crucial later in the semester and as we go on throughout the year. But one of the first ways that we were able to use these basic principles to really illustrate a lot of electronic behavior using what's called a cathodic ray. So the idea of this is you can go ahead and build up a negative charge on a cathode and a positive charge on an anode. The electrons are going to want to jump from the cathode to anode, but you can actually build a slit in the cathode. So when the electrons try to jump the anode, they miss and they keep going. And it's once they keep going is when you can actually do some really cool reactions on the electron as it travels through a vacuum. So what you've done by essentially having this hole is you've got this beam of electrons traveling through a vacuum, and it turns out that you can deflect these using a magnetic field, using the, not too surprisingly, called electromagnetic force. You can, and by having a positively charged plate and a negatively charged plate, you can generate a magnetic field, and the electrons will try and go towards the positively charged plate, indicating there's this interaction in between electrons and magnets. Now, one of the cool things is that this allowed the controlled use of electron beams, often called Cathodic rays. And this was very important in science, but it turns out it's also fairly useful in commercial electronics. As it turns out, if you have seen one of those big old bulky TVs, they essentially use the cathode ray, where you generate an electronic field and then send an electronic beam raging through a vacuum tube where it would hit a plate that would turn colors based on the energy of the electronic that hit it. This plate would then generate a series of field of colors in quick succession due to the rapid field of electrons hitting it, also called a television or a monitor or a screen. They essentially worked by using cathodic rays to selectively hit parts of the plate with different types of electrons. But a lot of this same science was also used to really investigate the properties of an electron. And while looking at these properties of the electron, one of the other big discoveries was Millikan, who essentially wanted to try and figure out the mass and charge of a single electron. Now, electrons are very small, so he had to be very careful in doing this. And what he used is this idea from a cathodic ray that electrons are going to be attracted to a positively charged plate. So what he did is he generated a whole bunch of oil drops that he then essentially hit with a high energy beam to essentially charge them. And so you have a whole bunch of oil drops, which have a slight negative charge going in between two magnetic plates. The more negatively charged the oil drops, the more they're going to want to go up to attract this positive plate. The heavier they are, the more they're going to want to fall down. And this let Millikan look at this kind of ratio of weight to charge. And by doing this, he was also finally able to figure out both of these quantities individually: the charge of the of individual electron and the mass of the electron. And essentially, the trick here was that he was able to quantize that that the charge worked in the charge and the mass essentially existed in certain concrete ratios. And by looking at these ratios, he was able to figure out the elementary charge of the electron, which also turned out to be very important, as this was the first time that someone was able to prove that the electron had to be an individual particle because it had a discrete mass and a discrete charge. And one of the most important things that he was able to prove in this, and it seems very logical now, but it was very revolutionary then, and that's that the mass of an individual electron is much less than the mass of an atom, which means that an electron is going to be part of an atom, and that the atom is not the most fundamental part of matter. The atom itself can be broken down, despite what the Greeks would tell you. And so, for example, the mass of an electron is about 9.1 times 10 to the negative 28th grams. Turns out that a hydrogen atom, the lightest atom, is much heavier. So a good way to think about this is that the mass of an electron is about 1/137th, so less than 1% of the mass of the lightest atom. Now, just because this experiment was done 100 years ago doesn't mean that people aren't still working on it. And so actually, over this last summer, a group was able to essentially repeat the Millikan oil drop, except for using radioactive labels so that you can see radioactive labels to help see the oil drop as it moves, and essentially lasers instead of magnetic fields to control the falling velocity. And so what you're seeing here is essentially the movement of a single oil drop with only a single electron moved, as it essentially rises against gravity due to that magnetic pole. So again, it's a quite cool set of experiments. And this, along with other experiments, really help show a very important thing. And that's that an individual atom essentially is going to have multiple electrons moving around in the atom. Now, the question is, well, exactly how are they moving? And if the electrons have a negative charge, where's the positive charge? So one of the first proposed models is called the Plum pudding model. Good proof that this is was proposed by an Englishman, because us Americans don't really have plum pudding. But a better way to think about this for an American is going to be the chocolate chip model. So imagine an atom like a chocolate chip cookie. We're going to have positive charge and negative charge. So Millikan essentially imagined the negative charges embedded in a field of positive charge, like chocolate chips in a cookie batter. So the electrons were going to be discrete, and the positive charge is essentially widely distributed. However, in order to test this, test the exact location of the positive charge, one of the things that you can do is shoot a positively charged particle at this atom and see how those positive charges interact. So 2 years after Millikan, Rutherford essentially constructed an experiment where you have a radioactive source which emits an alpha particle at essentially gold foil. And what they wanted to do was see how this alpha particle interacted with the nuclei. And one of the most important things to keep in mind, and we'll talk about this much later, is that the alpha particle is essentially a small +2 charged particle, and the gold atoms are going to be fairly big. They're going to have a lot of electrons. So if we have this plum pudding model, what we should see is that the alpha particles should essentially go through that very dispersed positive charge with no problem, and they won't really change directions. So we'd expect all of the particles to hit on the opposite side of the gold foil. Instead, what Rutherford found is some of the particles went straight through indeed, but some of them deflected at small angles, and some of them pretty much bounced right back. And they were able to measure this using essentially a detector. So you can actually do this experiment with pretty much old film paper, like that was used in film photography, as it will react to these radioactive particles. And you'll see essentially little spots of light. And I've actually performed this experiment. It's kind of fun. And so the problem is that when you're seeing this deviation of the alpha particles, what it's indicating is that all that positive charge is essentially discretely localized somewhere in the middle of the atom. Because when you have this concentration of positive charge, it's going to have a much greater impact on any incoming alpha particles. Most of the time, the alpha particles are going to be far enough away from this positive charge, it will go straight through. But sometimes it's going to, the alpha particles are going to come fairly close to the positive charge and deviate. And sometimes they're going to come straight on and bounce right back. And this was indeed what was seen. And Rutherford essentially labeled this nugget of positive charge as the atomic nucleus. Nucleus because it's at the nucleus or center of the atom. Now, one of the things that's actually really useful to note and was able to be determined by the Rutherford model is that the nucleus is actually quite small with respect to the total size of an atom. So good way to think about this is an atom is about 5 orders of magnitude larger than the nucleus. And this is a really big difference. It's kind of hard to internalize. So it's often done with analogies. And one of my favorites is, if I was going to have a nucleus about the size of a blueberry, the atom would be about the size of a football stadium. This is a big difference. This is the difference in between a nucleus at 10 to the negative 15th meters, so essentially about a femtometer, versus an atom that's about 0.1 nanometers. So a very big difference in the size of the system. So if you really want to think about what an atom is like, imagine putting a blueberry at the 50-yard line and then having a whole bunch of grains of sand, or essentially the electrons, as that would be kind of the relevant size, moving at an appreciable fraction of the speed of light rapidly around this football stadium. And that's one of the big things to note, is that while the nucleus is fairly small, one of the things that lets the atom be so big is those electrons moving at such high speeds that they're able to traverse the whole system fairly rapidly. And it becomes quite a precarious balance, which is going to drive a lot of chemical reactivity. Now, one of the things that is worth noting is while Rutherford just showed that the nucleus contains a whole bunch of positive charge, what he didn't show is that that isn't the only thing that it contains, because the nucleus contains both protons and neutrons. So the big thing to note about protons and neutrons is they both have about the same mass. However, only the proton contains positive charge. And one of the ways you can, which means that that I'll have a nucleus, there's going to be a mixture of positive charges held together by these neutral charged systems. So the way I tend to like thinking about this is positive charges don't like each other. So the nucleus is essentially made of a brick and mortar system. The protons are my bricks. The neutrons are essentially the mortar that helps glue the system together. And one of the things that is worth noting is as you put in more and more protons, you're going to need a slightly higher ratio of neutrons to essentially help make that positive charge stick together. And you'll see this as you work through these various systems. And again, how the neutron was really discovered is because of these differences in mass to charge ratios in many atoms. So let's say I'm looking at a typical hydrogen atom. So a hydrogen atom has an atomic mass of 1, which is going to be the same weight as a proton. So a hydrogen atom is essentially made of 1 proton and 1 electron. And that's kind of it. However, an oxygen atom has 8 protons. That's what defines an oxygen atom. However, it has an atomic mass of 16. So it has a weight that's twice as much as the number of protons, which means it should have about an even number of protons and neutrons. However, by the time you get to something like gold, it has 79 protons, but an atomic mass of about 197, meaning that it has about 118 neutrons, which is a big difference. So by the time you get to these heavy elements, you have more neutrons than you do protons in order to make all this positive charge stick together. And this is really kind of gets to the defining features of the differences in between different types of elements. It's mostly going to be defined by the differences in protons, but the neutrons do help distinguish some atoms from another. And this is a topic we're going to dig into with a little bit more detail next time. Until then, take care.